So this is Lab 3, Magnetic Field of a Bar Magnet by Annalee Anderson. The purpose of this lab was to measure the on and off axis magnetic fields due to a bar magnet and observe the distance dependence of the field. So for the lab procedure, first we located the magnetometer chip in our smartphones, and then we found found distances in which the magnitude of Bx, which is the x component of the magnetic field, equals a specific value. Then we calculated the distance dependence value known as N and the magnitude of the magnetic dipole moment. And then we calculated the magnetic field along the 45-degree axis and compared our observed value to the computed value in VPython. And then we found that the magnitude of the magnetic dipole moment was 5.063 ampere meter squared, and N was negative 2.3055. So first we located the magnetometer sensor so that we could then measure the distance from the sensor to the bar magnet for multiple values of the magnetic field. So we found the position in which the absolute value of Bx is at a max and By is at a min. And then we found the position in which the absolute value of By is at a max and Bx is at a min. And then for our fundamental principles, we know that the magnitude of the magnetic field due to a bar magnet decreases with increasing distance. And so we used this equation, and we know that K is a constant for our experiment, and then we measured the magnetic field at multiple distances from the bar magnet, and then we were able to solve for N, which should be negative in order to satisfy the inverse relationship between the magnetic field and the distance. And so for the application of the fundamental principles, we use this equation, and then if we took the natural log of both sides of the equation, we ended up with a y equals mx plus b equation, and then we were able to solve for N, which was negative 2.3055. And we should note that the expected value for N is negative 3, and so the percent error in our calculation was 23%. But we know that the value we obtained is due to experimental error. And then we were able to use this equation, and 3 in the above equation is replaced with the magnitude of N that we obtained, and then we were able to solve for mu, which was 5.063 ampere meter squared. And so for our graph, we have ln bx on the y-axis and then ln r on the x-axis. And you can see from this equation that the slope is our n, and then the y-intercept is our ln k. So for the measurements of the magnetic field on axis, we measured 3 distances at which the magnitude of Bx equals 20, 70, 120, 170, and 220 microteslas. And then the measurements for the magnetic field off axis, we found a perpendicular distance for which the magnitude of B net was equal to 100 microteslas, and then we repeated the process 3 times and found the average value for each individual measurement. And so some of our observations were that when the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction, and as the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. And so these observations confirm that the magnitude of the magnetic field due to a bar magnet decreases with increasing distance. And then we found the magnetic field along the 45-degree axis at a distance of 0.200347 meters. And so this is the value we obtained for our measured magnetic field, and this is the one that we obtained in VPython. And so here's the first part of my code. You can see that we created a function for the magnetic field using this equation right here. And then here is the second part of my code. And then here's my computational model. An important thing to note is that the arrows represent the magnetic field at different observation locations away from the bar magnet, which is represented by the white box. And so for the additional questions, what if you hadn't oriented your experiment to compensate for magnetic north and had instead laid out your meter stick at some intermediate angle with respect to Earth's magnetic field? How would your results have changed? So the values obtained for the magnetic field would be less accurate. There would be a significant difference between the experimental and theoretical values. Specifically, the values obtained for N, mu, and K would change. And also, what if you were to stick 2 identical magnets together end to end and run the experiment again? How would you expect your measurements to differ? And so we would expect that the magnitude of the magnetic field would increase, but the direction would stay the same. And so, in conclusion, the on-axis magnetic field of a magnetic dipole, in this case a bar magnet, points in the same direction as mu, and the magnetic field on an axis perpendicular to mu points in the direction opposite to mu. And finally, the magnitude of the magnetic field due to a bar magnet decreases with increasing distance. Thank you for listening, and I hope you enjoyed my video.